The universe is an endless gallery of wonders, a place where reality bends and twists into shapes so strange they defy everything we think we know. Picture a cosmic artist sketching rings of fire in the void, ghostly bubbles floating between stars, or a galaxy shaped like a spinning top, structures so bizarre they seem ripped from a dream. Yet these aren't works of fiction. They're real, they're out there, and they're waiting to unravel the secrets of the cosmos. Today, we're diving into 25 of the most mind-bending galactic puzzles ever discovered, each one a masterpiece of nature's ingenuity, each one holding clues to the universe's greatest mysteries. Imagine staring up at the night sky, not just seeing points of light but realizing those dots are threads in a tapestry of cosmic chaos. Some galaxies spin backwards, defying the rules of gravity. Others stretch like taffy into ribbons of stars, torn apart by forces we barely understand. And then there are the giant structures so vast they shouldn't exist, like the cosmic web's eerie filaments or the Great Wall of galaxies, a borderless monument stretching hundreds of millions of light-years across. These aren't just oddities, they're cosmic breadcrumbs leading us toward answers about dark matter, the birth of stars, and even the fate of the universe itself. What makes these structures so thrilling isn't just their strangeness, it's what they reveal about our place in the grand scheme. Every twisted ring, every inexplicable void whispers a question. How much of the universe's story are we still missing? From the haunting beauty of Hoag's object, a galaxy within a galaxy, to the violent elegance of quasars brighter than 1,000 suns, these puzzles remind us that space isn't just empty darkness. It's alive with mystery, daring us to look deeper, so buckle up. By the time we're done, you'll never see the night sky the same way again. The Hercules-Corona Borealis Great Wall doesn't just break records, it shatters our understanding of how the universe structures itself. Picture a tapestry of galaxies so immense it spans roughly 10 billion light-years, a structure so vast it would take light, the fastest thing in existence, 10 billion years just across from one end to the other. To put that into perspective, our entire observable universe is only about 93 billion light-years wide. This means the Great Wall isn't just big, it occupies a jaw-dropping chunk of cosmic real estate, dwarfing everything else we've ever discovered. But here's the real puzzle. According to the cosmological principle, the universe should look roughly the same in every direction when viewed on a large enough scale. Matter should be spread evenly, like raisins in a loaf of bread. Yet the Hercules-Corona Borealis Great Wall defies this entirely. It's a glaring exception, a concentration of galaxies so dense and sprawling that it throws our models into question. How did something this massive form so early in cosmic history? What invisible forces sculpted it? These aren't just academic questions, they're keys to unlocking the universe's deepest secrets. Discovered in 2013 by mapping gamma-ray bursts, the Great Wall revealed itself not through visible light but through the fiery deaths of massive stars. These bursts acted like cosmic breadcrumbs, tracing the outline of a structure too faint to see directly. And what they revealed was staggering, a filament of galaxies, galaxy clusters, and dark matter woven together in a pattern that shouldn't exist. Some scientists argue it might not be a single structure but a chance alignment, while others see it as evidence of undiscovered physics, perhaps even relics from the universe's infancy. One thing's certain, the Hercules-Corona Borealis Great Wall forces us to rethink the limits of cosmic architecture. If structures like this exist, what else is lurking in the unexplored depths of space? Could there be even larger formations waiting to be found, or is this wall the ultimate boundary? Every time we push the boundaries of our telescopes, the universe reminds us, it's far stranger, far grander than we ever imagined. The Boots Void is like a cosmic ghost town, a gaping hole in the universe so empty it defies logic. Stretching 330 million light-years across, This vast desert of space contains only a handful of galaxies where there should be thousands. To put that into perspective, if the Milky Way were placed at its center, we'd see almost nothing in every direction for distances that boggle the mind. It's not just a void, it's a staggering absence, earning its nickname, the Great Nothing. So how does something this empty even exist? One theory points to the early universe, where fluctuations during cosmic inflation, the rapid expansion right after the Big Bang, could have left behind patches of extreme low density. Imagine blowing up a balloon with uneven thickness. Some areas stretch thin, almost to the point of breaking. The Boots void might be one of those thin spots, a relic of the universe's explosive birth. But there's a wilder possibility. What if it's not natural? Some have speculated, though with no solid evidence, that an advanced civilization could have harnessed the energy of entire galaxies, leaving behind this barren expanse. While that's more science fiction than science, it highlights how baffling this void truly is. Even the few galaxies found within it seem oddly isolated, like lone survivors in an ocean of darkness. The real puzzle isn't just its size, but its defiance of cosmic statistics. Voids are common in the universe, but none come close to this scale. Most are 100 million light-years across at most, making the Boots void an outrageous outlier. Is it a fluke, or are we missing a fundamental piece of how the cosmos structures itself? Every time astronomers peer into its depths, they're met with more questions than answers. Perhaps the most haunting thought is this: the Boots void reminds us that the universe isn't just about what's there, it's about what isn't. In a cosmos teeming with galaxies, stars, and planets, this immense nothingness stands as a silent challenge to our understanding, a blank spot on the map whispering secrets we've yet to decode. The Sloan Great Wall stretches through the cosmos like a bridge between galaxies, a breathtaking filament of light and matter measuring 1.4 billion light-years from end to end. That's roughly 1/15 the diameter of the entire observable universe, an almost inconceivable scale that redefines our understanding of cosmic architecture. Discovered in 2003 by the Sloan Digital Sky Survey, this colossal structure isn't just another cluster or supercluster. It's a woven ribbon of galaxies, dark matter, and empty voids, defying expectations of how the universe organizes itself on the grandest scales. When we compare it to other massive formations, like the Hercules-Corona Borealis Great Wall, the Sloan Great Wall stands out not just for its size, but for its delicate balance. Unlike the dense Hercules-Corona structure, the Sloan Wall is more like a spider's web, galaxies strung along gossamer filaments, connected by gravity but separated by vast gulfs of space. This delicate arrangement challenges our models of cosmic evolution. According to conventional theories, gravity should have pulled these galaxies into tighter clusters over billions of years, not left them suspended in such an intricate, sprawling network. The real puzzle lies in timing. The Sloan Great Wall's existence suggests that matter began clustering into large-scale structures far earlier than we once thought possible. Some researchers argue that dark energy, the mysterious force accelerating the universe's expansion, may have played a role, counteracting gravity just enough to leave these filaments stretched but intact. Others propose that the wall is evidence of primordial density fluctuations, tiny ripples from the Big Bang frozen in time and magnified by cosmic expansion. But perhaps the most tantalizing question isn't how it formed, it's whether we're seeing a true physical structure or a trick of perspective. The Sloan Great Wall lies close enough to us that its light is only about 1 billion years old. That means we're seeing it as it existed in the distant past, when the universe was younger and denser. Could its apparent size be an illusion, a chance alignment of smaller structures viewed from just the right angle? Or does it hint at undiscovered physics, a hint that gravity behaves differently on scales we've only begun to explore? What's certain is this: the Sloan Great Wall forces us to confront the limits of our knowledge. It's a reminder that the universe doesn't follow tidy rules, it crafts its own. As telescopes grow more powerful, who knows what other colossal formations might emerge from the darkness, each one rewriting the story of how the cosmos builds itself. For now, this Great Wall stands as both a monument and a mystery, a challenge written in starlight. Hoag's object is the universe's most dazzling cosmic bullseye, a galaxy so perfectly symmetrical it looks like it was sketched by a celestial architect. At its heart lies a golden sphere of ancient stars, encircled by a flawless blue ring so precise it could be a ripple frozen in time. This isn't some artist's rendering, it's a real galaxy, floating 300 million light-years away, defying every expectation of how galaxies should form. Most galaxies spiral or clump chaotically, but Hoag's object is a mesmerizing exception, a cosmic oddity that's left astronomers scratching their heads for decades. The mystery begins with its structure. The core, packed with aging yellow stars, resembles a typical elliptical galaxy, while the outer ring blazes with young, blue stars and active star-forming regions. Between them, nothing. A dark, starless gap stretches like a moat separating the two distinct sections, a feature almost unheard of in other known galaxies. So how did this bizarre duo form? One leading theory points to a violent past, a galactic collision. Imagine a smaller galaxy piercing through a larger one like a bullet, its gravitational wake rippling the gas and dust into a ring where new stars ignite. It's a cosmic splash frozen in action, yet there's a problem. No remnant of the intruder galaxy has ever been found, leaving this theory on shaky ground. Another possibility involves resonance effects, where subtle gravitational nudges from the core could sculpt the outer disk into a ring over billions of years. Think of it like pushing a child on a swing at just the right intervals, tiny, timed forces that amplify into a dramatic motion. In Hoag's object, these rhythmic tugs might have herded gas and stars into that stunning circular formation. But even this explanation struggles to account for the sheer perfection of the ring, or why so few galaxies exhibit this flawless symmetry. Then there's the rarest idea of all, that Hoag's object is a failed polar ring galaxy. Some galaxies have rings orbiting at right angles to their main disk, likely from cannibalizing smaller neighbors. Hoag's ring aligns too neatly for this scenario, but what if it's a near miss, a glancing capture that settled into this eerie balance instead? It's a cosmic tightrope walk, a stability so delicate it borders on impossible. What makes Hoag's object even more extraordinary is its solitude. Most ring galaxies have neighbors, evidence of past interactions, but this one floats in eerie isolation as if it formed in a vacuum. That isolation deepens the enigma. Did it always look this way, or did some unseen event sculpt it into this pristine form? Even more tantalizing, telescopic surveys have revealed other, fainter ring galaxies in the distance, suggesting Hoag's object might not be alone in its strangeness. Could these be members of a rare galactic family or just cosmic coincidences? Every time astronomers study Hoag's object, they're confronted with the same humbling truth. The universe has a flair for the unexpected. This galaxy shouldn't exist, yet there it glows, a perfect loop of starlight challenging our theories of cosmic evolution. Is it a relic of some forgotten process or a signpost to physics we've yet to uncover? One thing's certain, in a cosmos full of chaos, Hoag's object is a quiet rebel, a reminder that nature's rulebook has pages we've barely begun to turn. The giant arc is a cosmic curveball, a structure so enormous it forces us to question the very foundations of modern cosmology. Stretching 3.3 billion light-years across the northern sky, this crescent-shaped string of galaxies and galaxy clusters shouldn't exist, at least not according to our best models of how the universe evolved after the Big Bang. Discovered in 2021 by astronomers analyzing the light of distant quasars, the giant arc isn't just large, it's a direct challenge to one of cosmology's bedrock principles, the idea that on the largest scales, matter should be spread evenly throughout the universe. What makes the giant arc so startling is its sheer scale. If you could hold a ruler to the sky, this structure would span roughly 1/15 of the observable universe, far larger than the Sloan Great Wall or even the Hercules-Corona Borealis structure. Its galaxies and clusters align in a subtle but undeniable curve, like a smile etched into the fabric of space-time. And that's the problem. According to the standard cosmological model, structures this vast simply couldn't have had enough time to form in the 13.8 billion years since the Big Bang. Gravity moves at a snail's pace across cosmic distances, making the giant arc's existence akin to finding a skyscraper in the Stone Age. Is it a statistical fluke? Some scientists argue that our perspective might be playing tricks on us, that the arc is just a chance alignment of smaller, unrelated structures seen from a particular angle. Imagine staring at a handful of scattered pebbles on a beach. From one spot, they might appear to form a line, but step to the side and the illusion vanishes. Yet statistical analyses suggest the odds of such a perfect alignment happening by pure chance are less than 1 in 20,000, turning skepticism into a numbers game where the universe seems to be cheating. But if it's real, the implications are staggering. The giant arc could hint at primordial irregularities in the early universe, like wrinkles in the fabric of space-time left over from inflation, the brief period of exponential expansion moments after the Big Bang. These wrinkles would have acted as cosmic blueprints, guiding matter into colossal structures far earlier than we thought possible. Even more radical is the possibility that the arc is evidence of something beyond our current physics, a sign that gravity or dark matter behaves differently on scales we've barely begun to map. The debate isn't just academic, it cuts to the heart of how we understand the universe's evolution. If the giant arc is confirmed, it could mean rewriting textbooks on galaxy formation, dark matter's role, and even the timeline of cosmic history. For now, it remains a tantalizing enigma, a curve in the cosmos that refuses to be ignored. Every new observation peels back another layer, leaving us to wonder, is this the exception that reshapes the rules, or just the universe reminding us how much we have left to learn? The dark flow is one of the most unsettling mysteries in modern cosmology, an invisible river of galaxy clusters all rushing in the same direction at breakneck speeds, as if pulled by some unseen hand beyond the edges of our universe. Discovered in 2008 by studying the subtle motion of hundreds of galaxy clusters, this phenomenon defies everything we thought we knew about cosmic expansion. Instead of drifting apart uniformly as dark energy pushes the universe outward, these clusters are caught in a silent current, streaming toward a point in space so distant we can't even see what's tugging them. What makes the dark flow so baffling isn't just the motion itself, but its scale. These clusters stretch across billions of light years, moving at speeds exceeding 1,000 kilometers per second toward a region in the constellations Centaurus and Hydra. That's like spotting every river on Earth suddenly flowing uphill, a coordinated defiance of gravity's usual rules. Even stranger, the pull seems to originate from beyond the cosmic horizon, the boundary beyond which light hasn't had time to reach us since the Big Bang. So what could possibly exert such a force from outside our observable universe? One radical explanation points to the multiverse. If other universes exist beyond our own, their gravitational influence might be leaking into ours, creating this vast directional pull. Picture a crowded room where everyone's pressed shoulder to shoulder. Even if you can't see your neighbors, you might feel their movements. In this scenario, the dark flow could be the cosmic equivalent evidence of a nearby universe nudging ours like a shadowy neighbor through the fabric of reality. It's a tantalizing idea, but one that dances on the edge of science fiction without concrete proof. Others argue the answer lies closer to home, hidden in our incomplete understanding of dark energy. This mysterious force accelerates the universe's expansion, but what if it isn't uniform, patchy variations in dark energy's strength could create uneven currents in space-time, herding galaxies like leaves caught in a cosmic wind. Or perhaps the dark flow is a relic of the Big Bang itself, a fossilized ripple from the universe's birth that set matter in motion before inflation stretched space to its current enormity. Critics, however, dismiss the dark flow as a measurement error or statistical illusion. They point to the cosmic microwave background, the afterglow of the Big Bang, which shows no clear evidence of such a massive directional bias. If the flow were real, they argue, its imprint should be visible in this primordial light. Yet newer studies continue to detect the signal, leaving the debate unresolved. The most chilling possibility, that we're staring at the gravitational footprint of something unimaginably vast, a structure so colossal it dwarfs the Hercules-Corona Borealis Great Wall, lurking just beyond the edge of sight. Whether it's another universe, a flaw in our theories, or something entirely unknown, the dark flow forces us to confront a humbling truth. The cosmos might be far stranger and far more interconnected than we ever dared to dream. Rising like ghostly towers from the heart of our galaxy, the Fermi bubbles are two colossal orbs of scorching gas and energy, each stretching 25,000 light-years into the void, half the width of the Milky Way itself. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these faint but furious structures glow with high-energy gamma rays, painting an eerie silhouette against the darkness. If our eyes could see them, they'd dominate the night sky, each bubble looming 15 times wider than the full moon. Yet despite their staggering scale, they remained hidden in plain sight until modern telescopes peeled back the curtain on their invisible light. What unleashed these titanic structures? The leading theory points to a cataclysmic tantrum from Sagittarius, a star, the supermassive black hole at our galaxy's core. Around 4 to 6 million years ago, this sleeping giant may have briefly awoken, devouring a massive cloud of gas or even a wayward star. The resulting explosion would have blasted twin jets of charged particles at nearly the speed of light, inflating these bubbles like cosmic balloons. You'd think such an eruption would leave scars across the galaxy, but here's the twist. The bubble's edges are razor-sharp, as if sculpted by some unseen force. That crispness suggests the event was shockingly brief, a cosmic burp lasting maybe 100,000 years, a blink in galactic time, but not everyone's convinced. Some researchers argue these bubbles could be the aftermath of a starburst frenzy, a period when the galactic center birthed thousands of massive stars in quick succession. Their collective supernova would have pumped energy into the surrounding gas, potentially creating the same towering structures. Yet there's a problem. The bubble's gamma-ray signature doesn't quite match what starburst models predict. The energy is too uniform, too symmetrical, as if shaped by a single titanic event rather than a chorus of explosions. Then there's the wild card, dark matter. If these elusive particles exist in dense clouds near the galactic center, they might occasionally collide and annihilate each other, releasing bursts of gamma rays. Could the Fermi bubbles be the smoldering wreckage of such an event? It's a long shot, but tantalizing enough that physicists keep running the numbers. The trouble is, no dark matter model perfectly explains the bubble's shape or their eerie symmetry, and until we understand what dark matter actually is, this idea remains in the realm of speculation. Perhaps the most unsettling puzzle is the bubble's silence. If Sagittarius, a star, truly erupted millions of years ago, where's the rest of the debris? Galactic eruptions usually leave behind shockwaves, heated gas, and other telltale signs, but the Fermi bubbles seem oddly self-contained. It's as if the galaxy tidied up after the party, leaving only these two lingering guests behind. Newer observations from X-ray and radio telescopes hint at fainter structures around the bubbles, perhaps echoes of older, even larger eruptions, now faded into the background hum of the cosmos. One thing's certain, the Fermi bubbles are a reminder that our galaxy isn't the quiet suburb it appears to be. Beneath its serene spiral arms lies a history of violence, a past where the heart of the Milky Way roared to life with enough force to reshape its surroundings. Whether they're relics of a black hole's tantrum, the ashes of dark matter, or something even stranger, these bubbles are a message in gamma-ray light. The universe is always more dynamic, more unpredictable than we dare assume. Deep in the cosmic past, colossal beacons of light pulse across the darkness, Lyman alpha blobs, some of the most enigmatic structures ever glimpsed in the early universe. These titanic clouds of hydrogen gas, spanning hundreds of thousands of light years, glow with an eerie intensity like ghostly lanterns hanging in the void. Their name comes from the specific wavelength of ultraviolet light they emit, a signature of hydrogen atoms being energized by some hidden power source. But what's truly staggering isn't just their size or luminosity, it's the fact that they shouldn't exist at all, at least not in the numbers we've observed. These blobs defy expectations, burning with a brilliance that theories struggle to explain. Imagine a cosmic nursery on steroids. Lyman alpha blobs are often found in regions teeming with young galaxies, their intense radiation likely playing a crucial role in shaping the universe's infancy. One prevailing theory suggests they're powered by the frenetic birth of massive stars, thousands of them igniting in unison, their ultraviolet light pumping energy into the surrounding gas like a neon sign buzzing to life. Another possibility points to supermassive black holes at the centers of primordial galaxies, their violent outbursts heating the gas to extreme temperatures. But here's the catch, even the most energetic star-forming regions or quasar eruptions can't fully account for the sheer luminosity of the largest blobs. Some of them shine with the brightness of 10 trillion suns, a radiation output so extreme it borders on the absurd. Then there's the puzzle of their structure. Unlike the chaotic swirls of most gas clouds, Lyman alpha blobs often exhibit eerie symmetry, their light distributed in smooth, bubble-like halos. Computer simulations suggest these shapes might be sculpted by dark matter, vast, invisible halos whose gravity draws gas into these luminous formations. Picture an invisible hand molding fog into glowing sculptures, their contours revealing the hidden scaffolding of the cosmos. Yet even this explanation leaves gaps. Some blobs appear to be connected by faint tendrils of gas, forming a cosmic web that hints at an even larger, interconnected system, one we're only beginning to map. The most tantalizing question isn't just how these blobs formed, but what they mean for galaxy evolution. Many astronomers believe they're the birthplaces of modern galaxy clusters, their gas condensing over billions of years into the stars and planets we see today. In this view, Lyman alpha blobs are the universe's construction sites, their radiant energy influencing how galaxies grow and interact. But others argue they might be cosmic dead ends, ephemeral structures doomed to dissipate, their energy too intense to settle into stable systems. Without more data, the blobs remain Schrödinger's galaxies, simultaneously seeds and specters of cosmic structure. What makes these glowing giants even more mysterious is their elusiveness. Detecting them requires peering back to when the universe was less than 2 billion years old, a task only possible with the most advanced telescopes. Each new observation peels back another layer, revealing complexities no model predicted. Some blobs rotate, others pulse in brightness. A few even appear to be cannibalizing neighboring galaxies, their gas glowing brighter where it collides with incoming material. It's as if each blob has its own personality, its own story to tell about the chaos of the early cosmos. The enigma of Lyman alpha blobs forces us to confront how little we understand about the universe's formative years. They're relics of a time when the cosmos was raw, violent, and unimaginably creative, a period when the rules of physics were tested in ways we're only beginning to grasp. Whether they're cosmic cradles or flash-in-the-pan anomalies, one thing is certain. These radiant ghosts hold secrets about how the universe went from simplicity to splendor, and unlocking them might just rewrite the story of everything. The Great Attractor lurks in the depths of space like a cosmic siren, tugging thousands of galaxies, including our own Milky Way, toward it with a gravitational pull so fierce it defies explanation. Hidden behind the dense starlight and dust of our galaxy's central bulge, this invisible behemoth remains one of the most frustrating puzzles in modern astronomy. We know it's there because everything around us is moving in its direction at mind-boggling speeds over 2 million kilometers per hour, yet we can't see it clearly due to what astronomers call the zone of avoidance, a blind spot created by the Milky Way's own galactic plane. Picture trying to study a lighthouse while standing inside another lighthouse's blinding beam. That's the challenge astronomers face. The zone of avoidance blocks our view of nearly 20% of the night sky in visible light, masking whatever mysterious mass lies at the heart of this gravitational disturbance. Early attempts to peer through this cosmic curtain using radio waves revealed a startling truth. The Great Attractor isn't acting alone. It appears to be just one piece of an even larger structure called the Laniakea supercluster, a web of galaxies spanning 500 million light-years, with the attractor serving as its gravitational center of mass. But here's where things get strange. Our current measurements suggest there aren't enough visible galaxies in this region to account for the tremendous pull. This discrepancy has led to two competing explanations. The first points to dark matter, the invisible scaffolding thought to make up 85% of the universe's mass. If concentrated in unprecedented densities around the Great Attractor, this mysterious substance could be amplifying its gravitational influence beyond what visible matter alone could achieve. The second, more radical theory suggests we're seeing the gravitational fingerprint of something even larger beyond our current observational horizon. A structure so massive it makes the attractor look like a local disturbance rather than the main event. Some calculations hint this unseen influence might be the Vela supercluster, a suspected galaxy megastructure still shrouded in mystery due to its position behind the zone of avoidance. Recent breakthroughs using X-ray telescopes have pierced through some of this obscurity, revealing dense clusters of galaxies in the attractor's vicinity that glow in high-energy light. These observations suggest the Great Attractor might not be a single concentrated mass, but rather a bulk flow, a vast region where the collective gravity of many galaxy clusters creates a sweeping current in the cosmic web. Yet even this explanation feels incomplete, as the observed mass still falls short of what's needed to explain the observed motion. What makes this gravitational enigma so compelling isn't just what we don't know, it's what its solution could reveal about the universe's structure. If dark matter is the culprit, studying the attractor might give us clues about how this shadowy substance clusters in space. If another unseen structure is the true puppeteer, we may need to rethink our models of cosmic evolution on the grandest scales. Every new observation peels back another layer, turning what once seemed like a simple gravitational anomaly into a Rosetta Stone for deciphering the hidden architecture of the cosmos. Astronomers now suspect the Great Attractor might not be our ultimate destination after all, just a waypoint in a much longer cosmic journey. Recent measurements suggest we're being pulled towards something even more massive in the Shapley supercluster, nearly 5 times more distant. This realization transforms the attractor from a singular mystery into part of a cascading series of gravitational influences, each revealing how interconnected the universe truly is. As we slowly map these unseen forces, one thing becomes clear. The universe doesn't just contain hidden masses, it's full of hidden relationships, a dance of gravity we're only beginning to understand. The Phoenix Cluster is a cosmic rebel, breaking every rule astrophysicists thought they knew about how galaxy clusters behave. At its heart lies a supermassive black hole surrounded by a swirling ocean of gas so hot it glows in X-rays, gas that should be cooling and collapsing inward to form new stars at a glacial pace. Yet when astronomers first studied this cluster in detail, they found something astonishing. Stars were being born at a rate of nearly 700 per year, over 20 times faster than in our own Milky Way. This isn't just unusual, it's a full-scale revolt against the standard cooling flow model that's dominated astrophysics for decades. Cooling flows were supposed to be cosmic slow dances. In most galaxy clusters, hot gas gradually loses energy, cools down, and trickles toward the center, where it might eventually form new stars, but only in modest numbers. That's because the supermassive black holes at the centers of these clusters typically act like cosmic blowtorches, pumping out jets of energy that reheat the gas and prevent runaway star formation. The Phoenix cluster, however, flipped this script entirely. Here, the gas is cooling so rapidly and in such vast quantities that even the black hole's feedback can't stop the stellar baby boom. It's as if someone turned up gravity's faucet to full blast while simultaneously muzzling the universe's usual enforcement mechanisms. What makes this cluster even more extraordinary is the sheer violence of its star-forming frenzy. Most galaxies produce stars in quiet, dusty cocoons, but the Phoenix cluster's nursery resembles a fireworks factory caught in an explosion. The gas isn't just cooling, it's plummeting toward the cluster's core at speeds exceeding 1,000 kilometers per second, a cascade so intense it's churning out massive, short-lived stars that burn bright and die young. Telescopes have detected enough raw material in this inflow to keep the party going for at least another 100 million years, suggesting we're witnessing a rare and fleeting phase of cosmic evolution, one that might explain how the universe's most monstrous galaxies grew so large so quickly. The implications ripple far beyond this single cluster. For decades, astronomers assumed black hole feedback was the universe's ultimate regulatory mechanism, a balancing act that kept star formation in check. The Phoenix cluster proves there are exceptions, windows of time when the scales tip violently in gravity's favor. Some theorists now suspect these episodes might be tied to the black hole's activity cycle, with periods of relative quiet allowing cooling flows to briefly overwhelm the system. Others propose that the cluster's extreme environment, its immense gravity and dense gas, creates conditions where feedback loops fail, like a thermostat breaking in an overheated room. But the biggest question isn't how this outlier exists, it's how many others we've missed. The Phoenix cluster was only discovered in 2010, hiding in plain sight among thousands of less dramatic systems. Could there be more like it, lurking in poorly surveyed regions of the sky? Or is this cluster the universe's way of showing us a forgotten chapter in galactic evolution, a time when gravity briefly wrested control from the forces that usually keep it in check? Every new observation peels back another layer, revealing a cosmos far more dynamic and unpredictable than our textbooks ever suggested. The Red Rectangle Nebula defies nature's usual preference for chaos, standing as one of the most geometrically perfect structures ever spotted in space. About 2,300 light-years away in the constellation Monoceros, this glowing cosmic artwork surrounds a dying star system with near-mathematical precision, its 4 bright spikes forming an almost perfect X shape, framed by glowing red rungs that resemble a celestial ladder. Most nebulae billow and swirl like smoke, but the red rectangle looks as if it were etched with a protractor, its symmetry so uncanny that astronomers initially suspected instrument error when first imaging it in detail. At the heart of this precision lies a cosmic dance between 2 stars, a dying red giant and its smaller companion locked in a tight orbital embrace. As the red giant sheds its outer layers in its death throes, the binary companion's gravity sculpts the ejected material into 2 opposing cones. From our vantage point, these cones overlap to create that striking X shape, while dust grains in the outflow scatter light to paint the nebula's signature crimson hue. But what makes this system truly extraordinary is the even spacing of those rungs crossing the X. These are thought to be shock waves, ripples in the outflow where gas compresses at regular intervals, like sound waves frozen in visible light. The result is less a nebula and more a cosmic xylophone vibrating with the rhythm of stellar demise. The nebula owes its stained glass appearance to a rare phenomenon, luminescence. Most nebulae glow because hot stars excite their gas, but the red rectangle's light comes from a process called extended red emission, where ultraviolet radiation from the central stars gets absorbed by complex organic molecules in the dust, then re-emitted as deep red light. These molecules, likely a mix of hydrocarbons and silicates, act like millions of microscopic prisms, diffracting light into the nebula's intricate patterns. It's nature's own kaleidoscope, powered by chemistry we're still unraveling. Astronomers suspect we're witnessing a brief, pivotal moment in stellar evolution. The red giant will soon exhaust its nuclear fuel, collapsing into a dense white dwarf while its expelled layers disperse into space. Within a few thousand years, a blink in cosmic time, the red rectangle's perfect geometry will fade, leaving only a diffuse cloud. That transience makes it a laboratory for studying how binary systems shape planetary nebulae and how complex organic molecules spread through the galaxy. Some even speculate these molecules could seed future planetary systems with the building blocks of life, yet mysteries linger. Why do the shock waves form such even spacings? How did the organic molecules become so abundant? And are there other, even more precise structures hidden in the dust? The red rectangle reminds us that even in death, stars can create staggering beauty, and that the universe's rulebook still has pages we've yet to read. At the heart of the small, unassuming galaxy NGC 1277 lurks a monster, a supermassive black hole so disproportionately large it's like finding a whale in a swimming pool. While most galaxies host central black holes that make up a tiny fraction of their mass, typically 0.1%, NGC 1277 Behemoth accounts for a staggering 14% of its entire galactic mass. That's a black hole over 10 billion times the mass of our Sun, crammed into a galaxy barely 1/10 the size of the Milky Way. A mismatch so extreme it's forcing astronomers to rethink how these cosmic predators grow. This bizarre outlier was discovered in 2012 when measurements of stellar velocities near the galaxy's core revealed stars whipping around at insane speeds, a telltale sign of something extraordinarily massive pulling at them. Further observations confirmed the truth: a black hole so outsized it shouldn't exist under modern astrophysical models. Normally, black holes and their host galaxies grow in tandem, with gravitational feedback regulating their expansion. But NGC 1277 black hole breaks that balance entirely, sparking a fierce debate over its origins. One camp argues this might be a relic black hole, a frozen fossil from the universe's chaotic infancy. In the early cosmos, before galaxies took their modern shapes, direct collapse black holes may have formed from the rapid implosion of giant gas clouds, bypassing the usual star formation stage. These primordial monsters could have grown to enormous sizes before their host galaxies had time to catch up, leaving them stranded in smaller galaxies like cosmic time capsules. If true, NGC 1277 black hole could be a rare survivor from this violent era, offering a direct window into conditions just after the Big Bang. Opponents of this theory point to an alternative explanation: runaway growth. Perhaps this black hole wasn't born oversized but became that way through a series of galactic mergers, gorging on gas and stars while somehow avoiding the feedback mechanisms that usually curb such gluttony. The galaxy's unusual structure, lacking the typical disk of younger stars, hints at a turbulent past where collisions or stripped material might have funneled an unusual amount of matter into the black hole's grasp. Simulations show that under just the right conditions, a black hole could steal mass from its surroundings faster than the galaxy can grow, creating this lopsided ratio. The implications stretch far beyond one odd galaxy. If relic black holes are real, they could explain perplexing observations like the existence of supermassive black holes in the very early universe, objects so massive they shouldn't have had time to form under conventional timelines. Conversely, if runaway growth is the culprit, it might mean our understanding of black hole galaxy feedback is incomplete, with hidden loopholes allowing for these extreme outliers. NGC 1277 isn't alone in this strange category. A handful of other galaxies, like Home 15A, also harbor suspiciously overweight black holes, suggesting these anomalies might be part of a broader cosmic pattern we're only beginning to recognize. Each new discovery chips away at the old assumptions, painting a universe where black holes don't always play by the rules, and where the most violent objects in existence might hold the keys to rewriting galactic history. The Andromeda Milky Way collision isn't some hypothetical cosmic event, it's already in motion, a slow-motion car crash set to unfold over the next 4 billion years. Right now, our galactic neighbor Andromeda is hurtling toward us at nearly 110 kilometers per second, a trajectory so precise that astronomers can predict the inevitable, a gravitational tango so immense it will reshape both galaxies forever. Picture two swirling disks of stars, each containing hundreds of billions of suns, drawn together by an invisible force until they merge into a single, chaotic masterpiece, a galaxy astronomers have nicknamed Milkomda. What's astonishing isn't just the scale of this collision, but how little it will disrupt individual star systems. Despite the mind-boggling speeds involved, the vast distances between stars mean actual stellar collisions will be vanishingly rare. Instead, the real drama lies in gravity's invisible hand. As the galaxies first graze each other around 3.75 billion years from now, tidal forces will stretch both into long, streaming tails of stars, celestial brushstrokes flung across the void. Some stars will be ripped from their orbits entirely, cast adrift into intergalactic space, while others will be flung into wild new trajectories, creating fireworks of star formation as gas clouds collide and ignite. The dance intensifies over the next 1 to 2 billion years as the galaxies swing past each other multiple times, their mutual pull drawing them closer with each pass. By 7.5 billion years from now, their cores, each home to a supermassive black hole, will finally spiral together, merging into a single, even more monstrous black hole at Milkomda's heart. The energy released in this final act will send shockwaves through the remaining gas, likely triggering one last burst of stellar births before the galaxy settles into its new elliptical shape, no longer a spiral but a smooth, glowing egg of stars. Yet for all the violence of this merger, Earth, if it still exists, might barely notice. Our solar system will likely be flung outward into the galaxy's outskirts, far from the crowded core where gravitational chaos reigns. The night sky, however, will transform utterly. Instead of the Milky Way's familiar band, future civilizations will gaze up at a dazzling, unrecognizable canvas, Andromeda's stars first appearing as a faint smudge before swelling into an ever larger spiral, eventually merging with our own into a single star-studded glow. What makes this collision so humbling isn't just its inevitability, but its role in the universe's grand cycle. Galaxies grow by consuming each other, and Milkomda will eventually meet the same fate when it collides with the next giant in our local group. These mergers aren't endings, they're cosmic rebirths, proof that even on galactic scales, change is the only constant. The Whirlpool Galaxy and its smaller companion, NGC 5195, are locked in a gravitational ballet that has sculpted their forms into cosmic masterpieces. While the Whirlpool's grand spiral arms dominate the scene, it's the smaller, irregularly shaped NGC 5195 that holds the key to understanding this dynamic duo's dramatic evolution. Their close encounter, so intimate that NGC 5195 appears to be tugging at one of the Whirlpool's arms, has sparked a frenzy of stellar birth and left both galaxies permanently altered. Every time these two galaxies swing past each other, their gravitational forces act like cosmic sculptors. The whirlpool's once symmetrical spiral arms now stretch into distorted arcs, their gas and dust compressed into dense knots where new stars ignite like fireworks. Meanwhile, NGC 5195 bears the scars of this interaction, its structure stretched and twisted into a chaotic mess of glowing gas and young star clusters. Astronomers call this process tidal disruption, where gravity doesn't just pull, it shears, stretches, and stirs the very fabric of galactic disks. What makes this pair so extraordinary is how clearly we can see the aftermath of their gravitational tug-of-war. The whirlpool's most prominent arm, the one seemingly connected to NGC 5195, glows brighter than the rest, packed with the blue light of massive, short-lived stars, a telltale sign of recent, intense star formation. This isn't just a chance alignment, it's direct evidence of how galactic collisions funnel gas into tight spirals, triggering stellar nurseries on a scale dwarfing anything in our own Milky Way. Yet the real surprise lies in the details. High-resolution observations reveal delicate feathers of dust stretching between the two galaxies, faint bridges of material torn loose during their closest encounters. Some of these filaments stretch for thousands of light years, fragile threads woven by gravity's invisible hand. Even more intriguing are the tidal dwarf galaxies, small, independent clusters of stars born from the debris of this cosmic dance, orbiting the pair like celestial satellites. This interaction isn't a one-time event, but a slow, ongoing process that has unfolded over hundreds of millions of years. Computer simulations suggest NGC 5195 has already plunged through the whirlpool's disk at least once, and it's destined to do so again, eventually merging completely in a distant future. Each pass ratchets up the chaos, driving more gas into star-forming regions while scattering older stars into elongated streams. The whirlpool system offers more than just a stunning visual, it's a living laboratory for understanding how galaxies evolve. By studying the ages of its star clusters, astronomers have pieced together a timeline of their encounters, revealing how these gravitational dances proceed in distinct phases. It's a reminder that galaxies aren't static islands but dynamic beings, constantly reshaped by their interactions. And perhaps most humbling of all, this same fate awaits our Milky Way when it meets Andromeda, a preview of the cosmic forces that will one day rewrite our own galactic story. The Sombrero Galaxy wears its cosmic disguise with such perfection it's fooled astronomers for decades. From afar, it looks like a classic elliptical galaxy, a smooth, featureless glow with a massive central bulge dominating its profile. But tilt your perspective slightly and the truth reveals itself. Delicate spiral arms wrapped around that bulbous core like lace on a brim, earning it the nickname the Sombrero for its striking resemblance to the wide-brimmed hat. This galactic hybrid defies easy classification, blending traits of both spiral and elliptical galaxies into a structure so unique it's become a Rosetta Stone for understanding galactic evolution. What makes this galaxy's anatomy so perplexing is the sheer scale of its central bulge. Unlike the modest bulges found in most spiral galaxies, including our Milky Way, the Sombrero's core is a monstrous sphere of ancient stars, accounting for nearly half its total mass. Imagine a city where the downtown district dwarfs all its suburbs combined, and you'll grasp the imbalance at play here. Telescope observations show this bulge isn't just large, it's spinning at dizzying speeds, a characteristic usually seen in disk-dominated galaxies, not ellipticals. This contradiction suggests a turbulent past, one that might involve galactic mergers, violent bursts of star formation, or even the insatiable appetite of its supermassive black hole. Then there's the enigma of its dust ring. Encircling the galaxy like a dark sash is an unusually crisp lane of cosmic dust, a feature so pronounced it stands out even in amateur telescope images. This ring isn't just decorative, it's a fossil record of the galaxy's history. Infrared studies reveal it's packed with complex organic molecules, the raw ingredients for star birth, yet the ring itself shows surprisingly little active star formation. It's as if the galaxy pressed pause on creation, leaving this reservoir of potential frozen in time. Some theorists propose the ring might be debris from a long-ago collision, a smaller galaxy torn apart and its remains smeared into this precise orbital path. Others suspect it's the result of internal dynamics, with the sombrero's own gravitational forces funneling gas and dust into this razor-thin plane. The sombrero's dual nature forces us to reconsider how galaxies grow and change. Most galaxies fall neatly into the spiral or elliptical categories, but this cosmic outlier suggests the universe enjoys bending the rules. One compelling theory posits that the sombrero might be a spiral galaxy caught in the act of transforming into an elliptical, stripped of its star-forming gas by encounters with other galaxies or by the relentless output of its active core. Alternatively, it could be the product of two galaxies merging, their distinct structures blending into this singular, breathtaking form. Every observation deepens the intrigue. The galaxy's outer halo contains globular clusters in numbers rivaling giant ellipticals, yet its disk maintains the ordered rotation of a spiral. Its X-ray emissions hint at a supermassive black hole far more active than expected for a galaxy of its type, as if it's refusing to settle into any one galactic identity. Even its distance is a puzzle. Recent measurements place it 29 million light-years away, nearly 5 million light-years farther than once thought, making its already impressive features even more colossal in scale. Perhaps the most striking lesson from the Sombrero Galaxy is how much we still don't understand about galactic diversity. It stands as a testament to the universe's creativity, a reminder that even the most familiar cosmic structures can harbor secrets that upend our expectations. Whether it's a relic of ancient mergers, a paused transformation, or something entirely undiscovered, one thing is certain. This hat-shaped marvel has more to teach us about the chaotic, beautiful processes that shape galaxies, and by extension, the story of everything. The Cartwheel Galaxy spins through space like a cosmic dartboard, its perfect rings rippling outward from a bullseye of brilliant blue stars, a celestial bullseye born from one of the most violent encounters imaginable. Roughly 200 million years ago, this spiral galaxy was minding its own business when a smaller intruder slammed through its core at ferocious speeds. The collision didn't just warp the galaxy's shape, it sent shockwaves through its structure, triggering a chain reaction that turned it into a living physics experiment. Gas and dust compressed into waves, like ripples spreading across a pond after a boulder plunges in, and along those crests, millions of stars ignited in clusters so bright they paint the galaxy's rings in sapphire light. This isn't just a fleeting cosmic oddity, it's a rare glimpse into a galactic metamorphosis. Most collisions trigger chaotic, asymmetrical distortions, but the Cartwheel's near-perfect rings reveal an almost textbook example of what astronomers call a density wave. As the smaller galaxy punched through, its gravity created a high-pressure zone that propagated outward, shoving gas inward toward the core while simultaneously compressing it into expanding circles. These dense rings became stellar nurseries, the pressure-igniting bursts of star formation that follow the wave's path like breadcrumbs. The outermost ring, stretching 150,000 light-years across, gleams with newborn stars less than 10 million years old, cosmic infants blazing with ultraviolet light. Meanwhile, the galaxy's original spiral arms, flung outward by the impact, now dangle like tattered ribbons, their stars scattered into the void. What makes this galaxy even more fascinating is its impermanence. Ring galaxies are cosmic mayflies. Their stunning structures last only a few 100 million years before gravity smooths them back into more conventional shapes. The Cartwheel's current phase is like a snapshot of a firework mid-explosion, capturing the moment when chaos and order briefly balance. Computer simulations show the intruder galaxy, now long gone, was likely a fraction of the cartwheel size, proving even small objects can unleash enormous transformation when they strike with precision. Yet the real surprise lies in the galaxy's core. High-resolution images reveal a second, fainter ring nestled inside the first, evidence of a rebound effect where some gas collapsed back inward before being shoved out again. This double-ring structure suggests the collision's energy rippled through the galaxy in multiple phases, like echoes in a canyon. X-ray observations add another layer. The core hosts a supermassive black hole, its appetite suddenly woken by the influx of gas, now spewing jets of charged particles that add to the galactic turbulence. The Cartwheel Galaxy is more than a pretty cosmic bullseye. It's a clockwork demonstration of how violence and beauty intertwine in the universe. Those blue rings aren't just stellar nurseries, they're pressure gauges, tracing the exact pathways where gravity and motion conspired to reshape an entire galaxy. As we watch it evolve, we're seeing the aftermath of a single, catastrophic moment frozen in time. A reminder that even in the vastness of space, nothing escapes the ripple effects of a well-aimed collision. The Tadpole Galaxy dangles through space like a celestial tadpole frozen mid-swim, its long, shimmering tail stretching an astonishing 280,000 light-years behind it, nearly 3 times the diameter of our entire Milky Way. This bizarre shape isn't some cosmic fluke but the scar tissue of a violent encounter that occurred roughly 100 million years ago, when a smaller intruder galaxy plowed through its disk with enough force to rip stars loose and fling them into this spectacular stellar stream. What remains is one of the most dramatic examples of galactic disruption ever observed, a slow-motion snapshot of gravity's destructive and creative power. Most colliding galaxies trigger bursts of star formation or warp into odd shapes, but the tadpole's fate was different. The intruder didn't just disturb its structure, it performed a gravitational slingshot maneuver, passing so close that tidal forces peeled off entire spiral arms like cosmic string cheese. The result is a tail composed of billions of orphaned stars, their once orderly orbits now stretched into this impossibly long ribbon winding through intergalactic space. Remarkably, these stars aren't scattering randomly. They're still bound by the tadpole's gravity, forming a coherent structure that glows with the collective light of countless suns. Infrared observations reveal the tail is surprisingly rich in dust and gas, meaning it's not just a graveyard of old stars but a potential birthplace for new ones far from their parent galaxy's core. What makes this stellar stream even more extraordinary is its sheer longevity. Unlike the chaotic debris of most collisions, which dissipates over time, the tadpole's tail has maintained its structure for eons because it's following what astronomers call a orbitally coherent path. Essentially, all its stars are moving in the same direction at similar speeds, like cars on a cosmic highway. This orderliness has allowed the tail to persist as a distinct feature rather than dissolving into the intergalactic void. Some stars along its length have even begun forming loose clusters, as if trying to build tiny new galaxies within the stream itself. But the real tragedy, or perhaps opportunity, lies in the fate of these exiled stars. Cut off from the tadpole's main disk, they'll never return home. Over billions of years, some may form new, ultra-diffuse dwarf galaxies along the tail's length, while others will drift forever in the darkness between galaxies. Ironically, the same collision that doomed these stars also enriched them. Spectroscopic analysis shows the tail contains heavier elements forged in the tadpole's pre-collision star factories, meaning these wanderers carry the chemical legacy of their birthplace into the cosmic wilderness. The Tadpole Galaxy isn't just a cautionary tale, it's a preview. In about 4 billion years, when the Milky Way collides with Andromeda, we might witness similar stellar streams arcing through space, though likely on an even grander scale. For now, this cosmic tadpole serves as a reminder that galaxies aren't immutable islands but dynamic structures, constantly reshaped by encounters that stretch across both space and time. Its shimmering tail isn't just debris, it's a monument to the universe's unending dance of destruction and renewal. The Medusa merger lives up to its ominous name, a cosmic tangle of two galaxies so violently entwined they resemble the writhing snakes of the mythical Gorgon's hair. Approximately 130 million light-years away in the constellation Ursa Major, this celestial collision has ripped apart orderly spiral arms and flung stars into chaotic streams, creating a structure that pulses with the furious energy of transformation. Unlike the clean rings of the Cartwheel Galaxy or the elegant tails of the Tadpole, the Medusa merger is pure bedlam, a snapshot of galactic destruction so intense it defies any simple classification. At the heart of this chaos lies a pair of supermassive black holes, each once the anchor of its own galaxy, now spiraling toward an inevitable collision. As they draw closer, their gravitational pull whips the surrounding gas into frenzied whirlpools, heating it to millions of degrees until it glows fiercely in X-rays. Meanwhile, the galaxy's original structures have been stretched into looping tidal tails, some stretching hundreds of thousands of light-years, where orphaned star clusters drift like embers from a fire. The resemblance to Medusa's serpentine locks is uncanny, but these aren't static tendrils, they're dynamic rivers of stars, gas, and dust still churning with the aftermath of impact. What makes this merger particularly fascinating is its asymmetry. One galaxy, a massive spiral, has largely survived the encounter with its core intact, while its smaller companion has been reduced to little more than debris, its stars scattered into the larger galaxy's gravitational field. Infrared observations reveal the aftermath, vast swaths of dust heated by newborn stars, their formation triggered by shockwaves compressing gas clouds into knots of stellar birth. In some regions, star formation rates have skyrocketed to 10 times that of our Milky Way, painting the merger in violent hues of blue and ultraviolet. Yet the real drama lies in the merger's future. Over the next few 100 million years, the two black holes will finally merge, unleashing gravitational waves powerful enough to ripple the fabric of space-time itself. The remaining gas will either be devoured by the newly formed supermassive black hole or expelled entirely, leaving behind a featureless elliptical galaxy, a far cry from the spirals that once existed. This metamorphosis isn't unique to the Medusa merger, but its current state offers a rare opportunity to study the process mid-transformation, like catching a caterpillar halfway through its chrysalis. For astronomers, the Medusa merger is more than a spectacle, it's a time capsule. The way its stars redistribute, the patterns of its gas flows, even the chemistry of its newborn stars all hold clues about how galaxies evolve when forced to share the same space. And while the merger's chaotic beauty won't last forever, its legacy will endure, a reminder that even in the vastness of the cosmos, no galaxy is an island. Every collision, every disruption, is just another stitch in the tapestry of the universe's unending evolution. The toothpick galaxy slices through the cosmic darkness like a razor's edge, its silhouette so impossibly thin that it defies our usual mental image of galaxies as sprawling, pancake-shaped spirals. Officially known as NGC 4565, this celestial needle lies about 40 million light-years away in the constellation Coma Berenices, presenting itself to us almost perfectly edge on a rare vantage point that transforms it into a masterclass in galactic anatomy. From this perspective, what would normally appear as a glowing disk of stars becomes a stark, elongated slash of light, its delicate dust lanes and star clusters laid bare like layers in an X-ray. What makes this galaxy's profile so mesmerizing isn't just its shape but the secrets it reveals. Most spiral galaxies hide their inner workings when viewed face-on, their dust and star-forming regions blurred into a messy glow. But the toothpick's edge on orientation lets us study its structure with astonishing clarity. A dark, jagged line of cosmic dust runs along its equator like a seam, the accumulated debris of billions of years of stellar births and deaths. Above and below this shadowy divide, the galaxy's bulge swells with the golden light of ancient stars, while its disk shimmers with the blue intensity of younger, hotter suns. This stark color contrast isn't just aesthetic, it's a timeline documenting the galaxy's evolution from its turbulent core to its quieter outskirts. Peer closer, and the toothpick's disk unveils even more surprises. High-resolution images reveal faint knots of light embedded within the dust-laden star clusters so young they're still cocooned in their natal gas. These stellar nurseries are rare in edge-on galaxies, as they're usually obscured by the very material that birthed them. Yet here, the angle of view lets us witness their faint glow, like embers glimpsed through smoke. Even more intriguing are the galaxy's flares, subtle warps in its outer disk, likely caused by gravitational tug-of-wars with smaller satellite galaxies or the lingering effects of ancient collisions. These distortions are cosmic fingerprints, evidence of the toothpick's dynamic history written in the bent paths of its stars, but the real marvel lies in the galaxy's sheer scale. Though it appears needle-thin from our perspective, the toothpick's disk stretches over 100,000 light-years across, comparable to our Milky Way, and its central bulge protrudes like a football wedged between two plates. This bulge isn't just for show. Its stars orbit in chaotic, random patterns, unlike the orderly rotation of the disk, hinting at a violent past where mergers or intense bursts of star formation scrambled its structure. Meanwhile, the disk itself is remarkably flat, its stars moving in near-perfect unison around the core, a synchronized dance orchestrated by gravity. Studying the toothpick is like flipping through a galactic textbook. Its dust lanes teach us how raw material cycles through galaxies, condensing into stars and then scattering back into space as those stars die. Its bulge offers clues about how galaxies mature, their cores growing denser and redder over time. Even its faint halo of globular clusters, ancient, tightly packed balls of stars, holds answers about the galaxy's earliest days, when it was just a cloud of gas collapsing under its own weight. Yet for all we've learned, this cosmic sliver still guards mysteries. Why is its dust lane so sharply defined compared to other edge-on spirals? How did its bulge grow so prominent without disrupting the delicate disk? And what unseen forces sculpted its outermost flares? Every observation peels back another layer, revealing how a galaxy's appearance, whether needle-thin or face-on, is just one frame in a much longer, far more dynamic story. The toothpick's elegance isn't just in its shape, but in the way it lays bare the hidden mechanics of galactic life, proving that sometimes the most revealing view is the one that leaves almost everything to the imagination. Mayol's object hangs in the cosmos like a celestial riddle, its bizarre question mark shape taunting astronomers with a puzzle that's defied explanation for decades. Officially catalogued as ARP 148, this enigmatic structure consists of a distorted ring galaxy attached to a long, curved tail, forming an uncanny resemblance to a punctuation mark etched in starlight. But this isn't just a quirk of perspective, it's a violent snapshot of a galactic collision frozen in time, a cosmic accident so rare it challenges our understanding of how galaxies interact. The leading theory suggests we're witnessing the aftermath of a direct hit, a smaller galaxy plunging straight through the heart of a larger spiral like a bullet through a clock face. The gravitational shockwave would have sent ripples through the victim galaxy's disk, compressing gas and dust into a ring where new stars ignite in a brilliant blue burst, while the intruder's own stars were shredded into that elongated tail. Computer simulations show such bullseye collisions can produce these exact loopy structures, but there's a catch. The angles have to be perfect, making Mayol's object a cosmic hole-in-one. Yet not everyone's convinced. Some researchers argue the object might instead be an extreme example of a polar ring galaxy, a rare breed where a ring of stars, gas, and dust orbits perpendicular to the main galaxy's plane, like a hula hoop around a bowling ball. These oddities usually form when a smaller galaxy gets torn apart and its debris captured into this precarious orbit. If true, Mayall's object could be a transitional phase, caught mid-formation before the ring settles into a stable plane. Supporting this view are faint tendrils of gas stretching between the ring and tail, hinting at complex gravitational interactions still playing out. The debate isn't just academic, it's a window into galactic resilience. The ring itself blazes with the blue light of newborn stars, proving how collisions can reignite dormant star-forming material, while the tail's reddish hue tells the opposite story, older stars stripped from their homes and left to fade into the darkness. This duality makes Mayall's object a living lab for studying how galaxies recycle their material, turning chaos into creation. Perhaps most intriguing is the object's impermanence. Simulations suggest the ring will gradually dissipate over a few 100 million years, leaving behind a misshapen elliptical galaxy, a fate shared by many mergers. But for now, this cosmic question mark lingers, a reminder that the universe's most profound mysteries often come wrapped in the simplest shapes. Whether it's a collision's direct aftermath or a fleeting phase in galactic evolution, one thing is clear. Mayall's object proves that sometimes the universe doesn't give answers, it only asks better questions. Hoag's object may be the poster child for ring galaxies, but it's far from alone in the cosmos, though its doppelgangers often turn out to be clever cosmic impersonators. Take the Cartwheel Galaxy, for example. Its stunning blue ring looks like a twin to Hoag's at first glance, but the resemblance is skin-deep. Where Hoag's ring floats in serene isolation, the Cartwheel's is a shockwave frozen in time, the aftermath of a smaller galaxy plowing through its center like a rock tossed into a pond. The difference lies in their birth certificates. Hoag's object appears to have formed without violent intervention, while the Cartwheel's beauty is literally trauma-induced. True Hoag-like galaxies are vanishingly rare, with fewer than a dozen confirmed across the observable universe. Their pristine rings demand near-perfect conditions, a stable core, a lack of disruptive neighbors, and just the right amount of gas to form a symmetrical circle without collapsing into spiral arms or clumping unevenly. It's the cosmic equivalent of balancing a pencil on its tip for billions of years. Most so-called ring galaxies are actually pseudo-rings, their loops forged in the chaos of collisions or gravitational disturbances. The galaxy NGC 6028, for instance, mimics Hoag's structure until you spot the faint remnants of spiral arms tucked inside its ring, the telltale scars of a near-miss encounter that stretched its disk into a loop without fully erasing its past. Gravity's artistry in crafting these imposters is both brutal and precise. When two galaxies interact, their gravitational dance can fling stars and gas outward, creating temporary rings that glow with newborn stars. The Medusa's Eye Galaxy NGC 4194 showcases this process mid-action. Its lopsided ring, studded with superstar clusters, is clearly the result of a recent merger, its asymmetry betraying its violent origins. Even the Milky Way hasn't escaped this phenomenon. The Monoceros ring, a disputed structure wrapping around our galaxy, might be the shredded remains of a dwarf galaxy torn apart by our own. What makes Hoag's object and its ilk so extraordinary is their defiance of this chaos. Their rings aren't accidents but enigmas, possibly shaped by resonant orbits or slow secular evolution over eons. Some theorists suggest they're the products of ancient bars, linear structures of stars that once spanned their cores which later dissolved, leaving behind these perfect circles like smoke rings from a vanished cigar. Others propose they're cosmic matryoshka dolls, with the outer rings being remnants of smaller galaxies swallowed whole and assimilated so neatly they left no visible trace. The rareness of true Hoag types isn't just a curiosity, it's a clue. Their scarcity implies the universe prefers messier, more dynamic structures where collisions and mergers drive evolution. Hoag's object and its handful of cousins might be cosmic white whales, their perfection an accident of circumstance rather than a common endpoint. Yet every new ring galaxy discovered, whether pristine or imposter, adds another piece to the puzzle of how galaxies transform, and how, in the right conditions, gravity can sculpt chaos into something breathtakingly symmetrical. Stretching nearly 300,000 light-years across the southern sky, the Magellanic Stream arcs behind the Milky Way like a cosmic umbilical cord, a shimmering ribbon of gas, dust, and scattered stars tethering our galaxy to its two largest satellite galaxies, the Large and Small Magellanic Clouds. This ethereal river isn't just a celestial landmark. It's the shredded remains of a gravitational tug of war that's been raging for billions of years, a cosmic crime scene where the Milky Way's relentless pull has slowly unraveled its smaller neighbors. What makes this structure so extraordinary is its sheer scale, enough gas to forge millions of stars, yet so diffuse it's nearly invisible except to radio telescopes. The stream's hydrogen atoms whisper their presence in faint radio waves, tracing a path that loops around our galaxy's south pole like a lasso. For decades, astronomers assumed this gas was torn entirely from the Magellanic Clouds as they orbited the Milky Way, but newer studies reveal a twist. The clouds themselves may have stolen some of this material from each other during close encounters long before the Milky Way got involved. It's a galactic soap opera with gravity playing the role of both villain and matchmaker. The violence of the stream's creation is written in its chemistry. Unlike the pristine hydrogen filling most of intergalactic space, this gas bears the fingerprints of stellar processing heavier elements like oxygen and silicon mixed in, likely blasted out by supernova in the Magellanic Clouds before being ripped away. Some sections glow faintly with the ionized light of ancient stellar explosions, while others are eerily dark, their molecules too cold and sparse to emit much radiation at all. This patchwork composition makes the stream a fossil record, its layers preserving distinct chapters in the cloud's turbulent histories. Yet the most tantalizing detail isn't where the stream has been, it's where it's headed. Simulations suggest much of this gas will eventually rain down onto the Milky Way's disk, a slow-motion deluge that could fuel a new wave of star formation in our galaxy's outer reaches. Already, astronomers have spotted clumps along the stream's length where gas is beginning to condense, as if the universe is teasing out the first drops of this impending downpour. If these pockets collapse further, they might form what's known as dark galaxies, invisible clouds of gas massive enough to be dwarf galaxies, but lacking the stars to make them shine. The Magellanic Stream's full story is still coming into focus. Recent observations reveal it's not alone. A fainter companion structure dubbed the leading arm arcs ahead of the Magellanic Clouds, as if the Milky Way's gravity is peeling them apart from both sides. Even more puzzling, the stream appears to be entangled with a much older, unrelated band of gas called the Fermi bubbles, the remnants of an ancient eruption from our galaxy's supermassive black hole. This unexpected interaction hints that the stream might be older than we thought, or that our galaxy's past outbursts have left invisible scars across its surroundings. One thing is certain, this shimmering river is more than a galactic accessory. It's a lifeline, a battlefield, and a time capsule all at once, proof that even in the vastness of space, no island is ever truly alone. The Virgo supercluster isn't just our galactic neighborhood, it's a single thread in a vast cosmic tapestry, woven from filaments of galaxies and dark matter so immense they redefine our sense of scale. Picture a spider's web stretched across billions of light years, its sticky strands replaced by rivers of galaxies streaming along invisible highways of gravity. These filaments form the backbone of our local universe, with the Virgo supercluster sitting at a bustling intersection where several of these threads converge. But here's the twist: what we see, the glittering galaxies, is just the icing on the cake. The real architecture lies in the unseen dark matter scaffolding that holds everything together, a hidden framework shaping the universe's grand design. Zooming out reveals an even more humbling truth. The Virgo supercluster is just one branch of an unfathomably larger structure called the Laniakea supercluster, a name from Hawaiian meaning immense heavens. Laniakea spans 500 million light-years and contains roughly 100,000 galaxies, all flowing like leaves on a cosmic river toward a gravitational focal point known as the Great Attractor. This motion isn't random, it's the result of dark matter's relentless pull, its tendrils knitting together galaxies into these staggering filamentary networks. The Milky Way, we're not just passengers on this ride, we're embedded in the cosmic web itself, orbiting the Virgo cluster's heart while being swept toward Laniakea's unseen center of mass. What gives these filaments their strength isn't just gravity, it's timing. Simulations of the early universe show that dark matter, ever so slightly denser in certain regions, began collapsing first under its own weight, forming a web-like skeleton before ordinary matter could catch up. Gas followed these dark matter trails, cooling and condensing into galaxies that now trace the filaments like fairy lights on a wire. The Virgo supercluster's threads, like the Pisces-Perseus supercluster filament stretching hundreds of millions of light-years, aren't static. They pulse with motion as galaxies slide along them, drawn into clusters where filaments intersect like cars merging onto a freeway. Yet for all their grandeur, these filaments are fragile. The space between them isn't just empty, it's a desert of vast cosmic voids, regions so devoid of matter that a single galaxy might be the only landmark for tens of millions of light-years. The contrast couldn't be starker. The filaments are the universe's bustling metropolises, while the voids are its abandoned frontiers. And just as cities grow from trade routes, the filaments owe their richness to the dark matter highways feeding them, funneling galaxies toward denser knots where they'll eventually merge into colossal clusters. Our place in this web isn't just happenstance, it's a front-row seat to evolution. The Virgo filament we're part of is still actively gathering galaxies, a process we can witness in real time by observing dwarf galaxies being torn apart by tidal forces as they fall toward the cluster's core. This isn't destruction, it's recycling, a galactic-scale reorganization where material is stripped, reshaped, and eventually reborn into new stars and systems. The same forces building Laniakea's filaments today will one day dissolve them, as dark energies accelerating push overwhelms gravity's pull, stretching the cosmic web into invisibility. For now, though, these filaments stand as the universe's most enduring artwork, a reminder that even in the darkest voids, connection is written into the fabric of space itself. Every galaxy, every star, every atom in our bodies traces back to these intricate threads, the silent scaffolding that's been shaping existence since the dawn of time. The bullet cluster isn't just another cosmic collision, it's a smoking gun for dark matter's existence, captured in a snapshot of gravitational chaos. This pair of galaxy clusters, caught mid-collision 1.4 billion light-years away, behaves unlike anything in everyday experience. When these titanic structures slammed into each other at millions of kilometers per hour, they're thousands of galaxies barely noticed. They're so far apart that most sailed right past one another like ghosts. But their hot gas clouds packed with visible matter weren't so lucky. These intergalactic atmospheres crashed together with such force they heated to hundreds of millions of degrees, glowing in X-rays like a cosmic traffic accident. Here's where things get weird. When astronomers mapped the cluster's mass using gravitational lensing, the way its gravity bends light from more distant galaxies, they found most of the mass wasn't where the X-ray glow concentrated. Instead, it hovered near the cluster's galaxy groups far from the gas. This discrepancy became the most compelling evidence yet for dark matter. Unlike ordinary matter, which interacts with light and gets caught in the collision's friction, the invisible dark matter sailed through unaffected, carrying most of the cluster's weight with it. Picture two crowds running through each other in a fog. The people galaxies pass unharmed. Their coats' dark matter stay with them, but their breath gas collides and lingers in the middle. The bullet cluster's dark matter map is etched in the warped light of background galaxies. Just as a wineglass distorts the view of a tablecloth behind it, the cluster's mass bends, passing starlight into faint arcs. By measuring these distortions, astronomers traced two distinct clumps of mass, each offset from the gas but perfectly aligned with the galaxies. This separation proves dark matter isn't just some theoretical placeholder. It's a physical substance that interacts gravitationally but ignores electromagnetic forces. Even more striking, the gas's slowdown matched predictions for ordinary matter's behavior, while the dark matter's trajectory showed no drag, as if it were untouched by the collision entirely. Critics once argued that alternative gravity theories might explain away dark matter, but the bullet cluster slammed the door on that idea. Modified Newtonian dynamics, OMND, which tweaks gravity's laws to eliminate the need for invisible matter, can't explain why the lensing signal would split from the visible gas. Only a particle like dark matter fits the observations, something that clumps around galaxies but doesn't scatter or slow like normal stuff. Later studies of other merging clusters, like MAX J0025.4-1222, reinforced this conclusion. Each collision showed the same telltale separation between visible and invisible mass. Yet the bullet cluster's story isn't just about proving dark matter exists, it's about revealing how it behaves. The fact that the dark matter halos stayed with their galaxies suggests it's cold, moving sluggishly compared to light. If it were hot and fast-moving, like hypothetical particles called sterile neutrinos, it would have smeared out during the collision. Instead, it stayed neatly clustered, supporting the leading cold dark matter model that underpins our entire understanding of cosmic structure. Even the cluster's collision speed, calculated at over 4,500 kilometers per second, became a tool for measuring dark matter's resilience. But the bullet cluster isn't done teaching us. Recent studies of its faint wake suggest dark matter might interact with itself ever so slightly, not through electromagnetism, but perhaps via some unknown weak force. Others scrutinize the precise shape of its halos for clues about dark matter's temperature, and as astronomers discover more of these cosmic pileups, each one a natural dark matter laboratory, the bullet cluster remains the gold standard, a celestial Rosetta Stone for decoding the universe's missing mass. Its violent beauty isn't just a spectacle, it's a roadmap to the invisible scaffolding holding everything together. The WOW signal remains astronomy's most tantalizing mystery, a 72-second burst of radio waves so powerful it convinced one researcher to scrawl, "Wow," in red ink on the data printout. Detected in 1977 by Ohio State University's Big Ear radio telescope, this narrowband signal blasted at 1420 MHz, the precise frequency hydrogen, the universe's most abundant element, emits naturally. It came from the constellation Sagittarius, vanishing as abruptly as it appeared, leaving behind decades of speculation. Was it a cosmic flare, a wandering comet, or humanity's first brush with an extraterrestrial beacon? For years, the extraterrestrial hypothesis simmered. The signal's intensity and frequency matched predictions for an artificial interstellar transmission, and its narrow bandwidth ruled out most natural astrophysical sources. Unlike pulsars or quasars, which emit across wide frequencies, the WOW signal was surgically precise, as if someone had tuned a cosmic radio to a single note. Even more compelling was its duration, exactly 72 seconds, the length of time the Big Ear telescope's fixed antenna could observe a point in space as Earth rotated. This eerie alignment suggested the signal was either timed deliberately or originated from a stationary source the telescope briefly scanned. Then came the comet theory. In 2016, an astronomer proposed that two passing comets, never previously catalogued, could have reflected sunlight into hydrogen-band radio waves as their icy surfaces vaporized near the sun. It was a creative solution except for one gaping flaw. The comets weren't in the telescope's field of view when the signal was detected. Worse, later analysis showed comet emissions couldn't produce such a focused, powerful burst. The debate reignited. If not comets and not earthly interference, researchers ruled out airplanes and satellites. What could explain a signal that appeared to target Earth's most obvious cosmic calling card? The plot thickened with the discovery of similar, unexplained radio bursts decades later. Fast radio bursts, or FRB, share the WOW signal's brevity and intensity, but their origins, neutron star collisions, magnetars, or even alien megastructures, remain contested. Yet none match the WOW signal's purity. Most FRBs scatter across frequencies, while the WOW signal's laser-like focus still stands alone. Some researchers argue it might have been an intercepted military transmission, but declassified records show no tests matching its profile. Others suggest a one-time celestial event, a neutron star's quantum flare, or a black hole's gravitational lensing of a distant signal, but these remain untestable without a repeat occurrence. Perhaps the most haunting possibility is that the signal was exactly what it seemed, a deliberate broadcast. The frequency choice, hydrogen's emission line, would be a universal handshake, a logical starting point for any civilization attempting contact. The fact that it hasn't recurred could mean the transmitter moved, shut down, or wasn't aimed at us at all. We might have intercepted a message intended for someone else, a cosmic letter lost in the interstellar void. The WOW signal's legacy isn't just about solving a puzzle, it's about confronting how little we truly know. In a universe teeming with natural radio sources, one burst defies all categories, lingering in the imagination as a reminder that some mysteries refuse to fit neatly into our textbooks. Whether it was a comet's whisper or a civilization's hello, its true lesson might be this: the cosmos still holds surprises no telescope can predict. These 25 galactic enigmas aren't just isolated oddities, they're pieces of a puzzle that keeps rewriting the rules of astrophysics. From the impossible vastness of the Hercules-Corona Borealis Great Wall to the perfect symmetry of Hoag's object, each discovery exposes the gaps in our cosmic playbook. They challenge the fundamental assumptions about how matter clusters, how galaxies form, and even how gravity behaves across unfathomable distances. The universe, it seems, delights in serving up exceptions that force us back to the drawing board. Consider how many of these structures shouldn't exist under our current models. The giant ark's curvature stretches the limits of cosmic evolution, while the boot's void's emptiness feels like a prank played by the cosmos itself. Dark flow tugs galaxies toward some unseen horizon, and relic black holes like the one in NGC 1277 stand as fossilized contradictions to our timelines. Even the ordinary becomes extraordinary under scrutiny. Collisions like the Cartwheel Galaxy show how violence births beauty, while filaments like those in the Virgo supercluster reveal the hidden scaffolding of reality. What binds these mysteries together isn't just their strangeness, but their insistence that we're missing something profound. Maybe it's a flaw in our understanding of dark matter, or perhaps dark energy works in ways we've yet to imagine. Could there be forces beyond gravity shaping the cosmos, or are we glimpsing echoes of conditions before the Big Bang? Every anomalous structure is a breadcrumb trail leading deeper into the unknown. The most exhilarating thought: this is just the beginning. For every galactic oddity we've catalogued, countless others likely hide just beyond our telescope's reach, structures so bizarre they'd make the Fermi bubbles look mundane. Future observatories like the Vera Rubin Observatory or the James Webb Space Telescope's successors will undoubtedly unveil new cosmic rebels that defy today's textbooks. So tell us, which of these cosmic conundrums keeps you awake at night? Is it the haunting perfection of the Red Rectangle Nebula or the gravitational audacity of the Bullet Cluster? Drop your favorites in the comments, and while you're at it, take a moment tonight to look up. Remember, every point of light out there holds mysteries we've barely begun to unravel, and the next great discovery might be hiding in plain sight, waiting for someone to connect the dots.